This is the second part of the presentation about TRIZ Foundations. So there are 5 key elements of TRIZ, and I've talked about the functionality element in the first part, and in the second part I will talk about the other 4 elements. So now I'm going to talk about resources. There are several categories of resources, and the first one is called substance resources. It includes all the substances that are involved in the process: raw materials, product, byproduct, system elements, and even including waste. So it's interesting that TRIZ thinks about waste as one of the resources. And then we also have field resources, which include all the energy that are involved in the system. And then we have also space resources, so whether it is empty spaces or interfaces of different systems or created by certain arrangement, those are all considered as resources by TRIZ. I think this is a nice example to see how we can utilize space to create more functions of an object. So this is a sofa, but then if you open up the seat, then inside you may put some bed and pillows so you can sleep on it. And when you're not using the bed, you can just pull down the cover and it becomes a couch again. So I think this is a very nice example. And then time is also considered as a resources, not only the time that we use to produce or use the product, but also the pre-work period and the post-work period. All the knowledge that we have and also all the knowledge that others have generated is also considered as resources. Finally, all the functions in the system are also considered as resources, including the unutilized, underutilized, and even harmful functions. Remember that one of the TRIZ ideas is that if you can turn these harmful functions into useful functions, then you created an invention. Now the next element in TRIZ is called ideality. So in TRIZ, ideality is defined by the division of benefits by the sum of cost and harm. By benefits, TRIZ means that it is the sum of all the values of the system's useful functions, divided by all the costs and all the harm. One thing to notice here is that the supporting functions are not considered to be useful functions. So all the supporting functions actually is considered as cost. And then the ideal final result is that the ideality should achieve infinity. It means that we may gain all the benefits without paying any cost and then without any harm. So of course, this ideal final result sometimes or most of the times is not realistic, but it should be something that we try to achieve. We want all the benefits with zero cost and zero harm. The next important element in TRIZ is called contradiction. There are 2 types of contradictions: technical contradiction and physical contradiction. So technical contradiction happens when you try to improve one attribute of the system, but then it makes the other attribute of the systems worse. Or it can also happen when you have some useful action in your system, but that useful action at the same time also produce something harmful. The contradiction may also happen when you try to introduce a new useful function. It causes the overall performance of the system becomes worse. So the common example here includes something like when you try to add the productivity, the accuracy of the production will suffer or become worse. Or when you try to add the reliability of the system, then the systems become more complex. However, Altshuler found out that Actually, among all contradictions that he has seen in the products and services, actually there are only about 1,250 typical contradictions. And then even better, these contradictions may be described by 39 design parameters. So he saw a lot of contradictions, but then those contradictions may be summarized into 1,250 typical contradictions, and it may be further described by 39 design parameters. TRIZ developed tools to solve these contradictions based on these 39 design parameters. So these are the 39 design parameters that may be used to describe the typical contradictions that happen in the systems. Now let's see the other type of contradiction, which is called as physical contradictions. In physical contradictions, we have a contradiction when to perform function 1, an element must have property or characteristic P. However, to perform function 2, the same element must have the property of minus P, or in other words, the opposite of P. So the same element, when you use the product for the first function, it needs to have the characteristic P. However, when you use the same product for the other function, this element needs to have a property that is the opposite of the first property. So an element has to have a property P and minus P. So let's see the case where physical contradiction happens. In the production of an electrotechnical wire, the wire first goes through enamel liquid. Once it has been covered by the enamel liquid, it goes into the die. The die will remove the excess of the enamel and then size the wire. To do this accurately, the die must be in hot condition. However, problem happens when the wire feed is interrupted for several minutes. So if somehow there's a problem and the wire feed needs to stop for a moment, then the hot die will cause the enamel bake and destroy the wire. So because the wire feed stops, so the heat will cause the enamel here destroy the wire. So in order to continue the process again, then the workers must cut the wire and clean the die. So the physical contradiction here is that the die should be both hot and cold. It should be hot when the production is going, but then it should be cold when the production stops whenever there is some problem happen. So that is the physical contradiction. The die must be hot, but the die must be cold either in different condition. The fifth element in TRIZ is called evolution. So TRIZ researchers found out that the evolution of technical systems are very similar to each other. So almost all systems, they follow this pattern. And then since they follow the same pattern or trend, it becomes predictable if you are at this stage and you know what should happen next. So the trend follow S-curve, which is shown here. It starts with the infancy, where the system is still inefficient, unstable, and so on. And in the growth system, there's a lot of improvement starts to happen. And then in the maturity, only small improvements and trade-offs are happening. And then in the decline stage, this technology is kind of forgotten because people do not need this anymore, or a newer function already appears. So this curve is called an S-curve. So again, if you know at this point which part of your product is in, then you may predict which stage that your product will be in the next couple of months or years. And then the best thing to do is actually when it's still when the first system is still in the growth phase, we start developing the second system, such that when the first system reach maturity and starting to decline, we are already in the second system that is already growing. So those were the 5 key elements of TRIZ. Now let's see how actually TRIZ solve problems. TRIZ offers a 4-step process. So the methodology in TRIZ offers a 4-step problem definition and problem solving process. The most important part of this 4-step process is the first one, problem definition. And then among the components of the problem definition, the most important one is functional analysis. Means that you really need to carefully define what are the functions, what are the substances involved in the function, what are the relation between them, whether it's normal, insufficient, excessive, harmful, or so on. So you really need to define the function carefully and in very good detail. Once you have defined the problem, you may classify the problem and select the tool based on the TRIZ suggested tools. Once we have selected the tool, we can generate the solution, and finally we can do the evaluation on the solution alternatives. To help us defining a problem, we may ask ourselves or the team these 4 questions. What is the problem? What is the scope? What subsystem, system, and components are involved? Do we have a current solution? If we do, then why is the current solution is not good enough? The possible tools to help us defining the problems are: we can do functional modeling and analysis. We can draw the functional analysis diagram. Then we can use the ideality and IFR concept to see how far we are from the ideal solution and to see what kind of ideal solution that we have. We can also see how far we are in the technology evolution by looking at the S-curve analysis and think about which part of this curve our product is currently in. And then we can also do contradiction analysis to see if there is any technical or physical contradiction when we try to improve our system. Once you have identified the problem, TRIZ actually may suggest some methods or tools to solve that problem. For example, if you have physical contradictions, then TRIZ have physical contradiction resolution and separation principle to solve that problem. If you have technical contradiction, TRIZ also have principles to solve it. If you have imperfect functional structures, which means that your useful function is not enough, or you have excessive harmful function, again, TRIZ has the tools. For excessive complexity, TRIZ suggests trimming and pruning. For system improvement, TRIZ suggests us to look at the evolution of technological systems. And finally, when we know that we have to develop the new functions, but we have no idea where to start or how to create them, then TRIZ has physical, chemical, and geometric effects database to help us solving this problem. I'm going to discuss this problem and the corresponding tools in the next presentation. In the next step, we use the suggested TRIZ tools to help us generate the solution alternatives. And then once we've got all the alternatives, we may apply the evaluation method to select the best alternatives. So that's the end of the first presentation. I'm going to talk about these tools and about the examples in the next presentation. If you have questions, feel free to leave your questions in the comments or send me an email or a message through IDE. Thank you.